So we're going to start studying electric fields. Electric fields are just a region of space around some charged object, which we really can't see with our eyes, but we can give a visual representation to see how charged particles and really uncharged particles might interact based on the field that they're actually in. It's very similar to like a gravitational field. We can't really see it, but we can predict and see the results of particles being within that field based on them being pulled towards objects with gravity. Right? So an electric field is an area around a charged object, and really it's going to produce some electric force on charged or uncharged objects within that. And so the first thing we're going to understand is just the direction of the field. The field is really based on the direction that the electric force would be on what's called a test charge. So a test charge is just if we had a small particle that was also charged in the positive, that was so small that it really wouldn't counteract the electric field that's created by this positive charge. It's kind of like we have gravity and we are in a gravitational field, but our mass is so small that our gravitational field of us really doesn't affect the overall gravitational field of the Earth. All right? So if we think about this, these two are like charges, so they would repel, so the electric force would be pointing away. So the electric field around a positive charge is pointing away from it. Same idea, have that same test charge there, small particle of charge. Around a negative charge, it would be attracted to it. So the electric force would be towards the particle. So we draw negative electric fields as pointing towards that which is producing it. Okay? We also can indicate the strength of the electric fields simply by the density of the field lines that we draw. The more field lines, the stronger the charge. So this is creating now a charge that has a stronger electric field. Whereas if we were to erase some of the field lines over here, that would be an electric field that now has a weaker electric field just simply based on the density of the lines. It's not something you can, again, see with your naked eye, so we try to represent it as best we can based on the density of the fields. Sticking with the idea of just visualizing electric fields, they also can interact with one another. They are vectors, and we'll talk about that here in just a second. But if we have a positive and a negative charge, those fields will interact and they will actually form a shape that looks something like that. A key point with looking at this though is that no matter what, the electric field should be perpendicular at the point of which it touches the particle which it's coming towards. Right? So the electric field is always perpendicular to the surface of that which is producing the electric field. So here we see the electric fields and they're kind of coming together. Here we have electric fields and they're actually kind of pushing apart, or they're creating a place where there is no electric field. And that can make sense because it doesn't matter if we have a positive charge or negative charge here, they're not going to experience any electric force, or a net force, I guess I should say. They would experience an electric force. It would have a repelling force from this one and a repelling force from this one, and so the net force of those would actually be zero. So there is not a region where it would feel a net electric force. If this was negative, it would be attracted towards both of them. So they would still have a net force of zero. So there can be a region where there is an absence of an electric field, even though we have charged particles around it. Now, when we calculate electric fields, there's actually two main ways we can calculate it, but I want to make sure we understand what we're actually calculating first. So an electric field tells us the force per unit charge of what we're going to experience. So if we have an object that's positive, and it's going to create an electric field, here's what we know. If we are a certain distance, r, from that, we're going to experience a certain amount of force per unit charge. So how do we find that? So the electric field E, is the force per unit charge that we would experience. Right? So let's imagine we have another positive charge there. Well, how would I find that force? And here's what I'm going to do. I'm going to indicate the force created in the field with a capital Q, and the force in the field with a lowercase q. So my force would be Coulomb's constant, force creating the field, charge in the field over r squared divided by the charge that's in the field. Okay, so force per unit charge, what we see is these Q's are going to cancel each other out. And so we get that the force, or excuse me, the electric field can be calculated as K Q over R squared. And this is the charge in the, or creating the field. So one equation is going to be this one. And that's only if we know that this capital Q, the charge that's actually creating the electric field. The other equation that you'll use is this one that we started with. The only difference is you can only use this equation if we know the force that is acting and if we know the charge that's in the field. So it is not the charge that is creating the electric field, but it is in the field. It is typically a smaller charge than that of capital Q. All right, so those are the two main equations that we're going to use when we're dealing with this.